Without getting into a detailed discussion of the mathematics behind cryptography, its application as a security technology is an important consideration in managing network security. But first, let's talk about the basics. Encryption is the process of converting a readable message into a form that cannot be understood by unauthorized individuals or systems. Decryption is the process of converting an encrypted message back to its readable form. Plain text is the form that is readable by individuals or systems. And ciphertext is the form that is not readable by individuals or systems until it is decrypted. Cryptology is the science of encryption and encompasses two sub-disciplines: cryptography and cryptanalysis. Cryptography, from the Greek words kryptos, meaning hidden, and graphein, meaning to write, describes the process involved in encoding and decoding messages so that unauthorized individuals cannot understand them. Cryptanalysis, from analyzein, meaning to break up, is the process of deciphering the original message or plain text from the encrypted message or ciphertext without knowing the algorithms or keys used to perform the encryption. Cryptography works by combining a number of simple functions to take the bits or blocks of data transmitted over media and scrambling them up or swapping them out with other bits. This involves three basic components: the data stream, the mathematical algorithm or function, and a key. The key is additional information used to encrypt and decrypt the information. Without the key, you can't decrypt an encrypted message. Some keys are simply the method of how the data is encrypted, such as swapping out every letter in the alphabet with the third letter to the right. Other keys are sets or blocks of data that are used in the mathematical functions to change the data. In encryption, the three most commonly used functions are substitution, transposition, and XOR. In a substitution cipher, you substitute one value for another. In this example, the plain text is converted into the ciphertext by shifting each letter 3 letters to the right, so that A becomes D, etc. A monoalphabetic substitution, like this example, uses only one alphabet, while a polyalphabetic substitution would use 2 or more alphabets. The transposition cipher, also known as a permutation cipher, simply rearranges the values within a block to create the ciphertext. This can be done at the bit level or at the byte or character level. In this cipher, the character in position 1 is moved to position 4. In the XOR cipher conversion, the bit stream is subjected to a Boolean XOR function against some other data stream, typically a key stream. XOR is simple. If the two values are the same, you get a 0. If not, you get a 1. This process is reversible. That is, if you XOR the ciphertext with the key stream, you get the plain text. There are two general categories of encryption functions: symmetric and asymmetric encryption, but there are also hybrid versions as well. Symmetric encryption uses the same algorithm and key to both encipher and decipher the message. This is also known as private key encryption. Symmetric encryption methods are usually extremely efficient from a computer processing standpoint. But the challenge in symmetric key encryption is getting a copy of the key to the receiver, since the same key can be used to both encrypt and decrypt the ciphertext. This requires that the key exchange be conducted out of band to avoid interception. The current industry and government standard in symmetric encryption is the Advanced Encryption Standard, or AES, which uses a block size of 128 bits and a key length of either 128, 192, or 256 bits. This means that the block or set of data used in each iteration of the encryption process is 128 bits long, and the key used in the mathematical function can be either 128, 192, or 256 bits. The longer the key, the stronger the encryption. In this example, the sender has a message he'd like to send to the receiver. He has a private key that he uses to encrypt his message. He sends a copy of the private key to the receiver in an out-of-band communications, like a courier or separate email account. He then sends the encrypted message via email or other media, and the receiver then uses the key to decrypt the message. Asymmetric encryption, also known as public key encryption, uses two different but mathematically related keys, either of which can be used to encrypt or decrypt the message. However, if key A is used to encrypt the message, only key B can decrypt it, and vice versa. This technique is commonly used in public key encryption where one of the keys is private or held by the organization and the other is public, as in stored in a public holding site where anyone can get it. This allows the organization to communicate secretly with anyone, as the outside party can get the public key and use it to encrypt messages which can then only be read by someone with the private key. The most popular asymmetric encryption standard is known as RSA, which are the initials of the three scientists that developed it: Rivest, Shamir, and Edelman. It uses key sizes in the 1 to 4 kilobit range. The problem with asymmetric encryption is that it requires 4 keys to hold a single conversation between two parties, and the number of keys grows geometrically as parties are added. Asymmetric encryption is also computing intensive, meaning it's not very efficient or fast processing by a computer. In this example, the sender has a message he'd like to send to the retriever. He first retrieves the receiver's public key from a public key repository. He uses the public key to encrypt his message. He then sends the encrypted message via email or other media to the receiver. The receiver then uses his private key to decrypt the message. Asymmetric encryption also has an interesting use. If you reverse the process and encrypt a message or the hash of a message using your private key and attach the encrypted portion to the plain text version of the message, and then you send that message to anyone, it can be proven to be an authentic message from you by simply taking your public key, decrypting the attached encrypted piece, and comparing it to the plain text message or its hash value. This is the basis for digital signatures, which provides a function known as non-repudiation. This simply means that you can't claim it's not your message, but it's also a function of, yes, I can prove that it's my message and it's authentic. When combined with the hash function, it's also proof that the message hasn't been altered. There are third-party organizations that handle that validation, known as registries, that will certify a digital signature is authentic. Public Key Infrastructure, or PKI, is an entire set of software, encryption, organizations, and protocols that enable secure communications and online business. PKI systems are built on asymmetric encryption and use components called digital certificates and certificate authorities to verify the authenticity of vendors and their customers. PKI provides authentication. Individuals, organizations, and web servers can validate the identity of each of the parties in an internet transaction. Integrity. Content signed by the certificate is known to be unaltered while being moved from host to host or server to client. Privacy. The information is protected from being intercepted during transmission. Authorization. The validated identity of users and programs can enable authorization rules that remain in place for the duration of a transaction. Non-repudiation. Customers or partners can be held accountable for their transactions, such as online purchases, which they cannot later dispute. A typical PKI solution protects the transmission and reception of secure information by integrating the following. Digital certificates are public key container files that allow computer programs to validate the key and identify to whom it belongs. Certificate authority, which issues, manages, authenticates, signs, and revokes users' digital certificates, which typically contain the username, public key, and other identifying information. Registration authority, which operates under the trusted collaboration of the certificate authority and can handle day-to-day certification functions, such as verifying registration information, generating end-user keys, revoking certificates, and validating user certificates. Certificate directories, which are central locations for certificate storage that provide a single access point for administration and distribution. Management protocols, which organize and manage the communications between CAs, RAs, and end users. Policies and procedures, which assist an organization in the application and management of certificates, the formalization of legal liability and limitations, and actual business trade. Since symmetric is fast but difficult to share keys, and asymmetric is secure from the beginning but slow, it's only logical to combine the two by initially using asymmetric encryption to share a symmetric key, known as a session key, and then use that session key for the rest of the conversation. The most popular hybrid system used for this purpose is the Diffie-Hellman key exchange method, which provides a way to exchange private keys using public key encryption without exposure to any third parties. In this example, the sender has a message he'd like to send to the receiver. He first retrieves the receiver's public key from a public key repository. He then uses the public key to encrypt a symmetric private key or session key. He then sends the encrypted session key via email or other media to the receiver. The receiver then uses his private key to decrypt the sender's private key, which is then used in all subsequent communications. While modern crypto systems can certainly generate unbreakable ciphertext, that's only possible when management makes sure the proper key management systems are being used and when the crypto systems are operated and managed correctly. For those organizations with the need and the capability to use cryptographic controls, they can be used to support several aspects of the business. The confidentiality and integrity of email and its attachments, authentication, confidentiality, integrity, and non-repudiation of e-commerce transactions, authentication and confidentiality of remote access through VPN connections, and a higher standard of authentication when used to supplement access control systems.